In this video, we're going to be talking about optimization, which is one application of the derivative. In previous lessons, we learned the extreme value theorem. Remember, the extreme value theorem said that if a function was continuous and its domain was a closed interval, then its range would also be a closed interval. In other words, continuous functions defined on a closed interval will achieve their absolute maximum y value and their absolute minimum y value. We also learned the first derivative test for finding local maxes and mins, and the second derivative test is an alternative test for the same thing, finding local maxes and mins. The objectives for this lesson are to learn the general problem-solving strategy for optimization and then use it to maximize and minimize quantities such as area, distance, volume, surface area, time travel, revenue, etc. So here is our strategy. And I've tweaked it a little bit different than our textbook, but they're essentially the same. Optimization. So first you want to, anytime with a word problem, you always want to read it a few times, take the pressure off yourself to instantly know how to do the problem. Just make sure you understand what it's giving you and what it's asking you to find. And sometimes if the problem is geometric, it's often helpful to draw a picture. Then once you've identified your givens and unknowns, you need to introduce some notation. You need to let X be the length of fencing or whatever, right? You need to introduce some letters to represent quantities. Now you want to relate your variables. How are they related to each other? One, your objective function. That's the function that you want to maximize or minimize. So it'll say maximize the revenue or maximize the profit or minimize the cost or minimize the surface area, right? Anytime the word problem uses the word maximize or minimize a particular quantity, they've told you the objective function. Now, usually the objective function is going to depend on more than one variable, and so you're going to need to use your constraint equation to relate the variables. We're trying to make a fence, but we only have, we're trying to make like a yard, but we only have so much fencing. Okay, the length of that fencing, in other words, the perimeter of the yard would be a constraint, right? And so then you're going to use that constraint equation and substitute it into your objective function. So your objective function is a function of just one variable. If it is appropriate, not always the case, but if it's appropriate to identify the domain of that objective function, you want to try to go ahead and do so. So now we're looking at our objective function, and if we know the domain is a closed interval and the objective function is continuous, then you can go ahead and use the closed interval method for finding absolute maxes and mins. That is just a result of the extreme value theorem, right? Right up here. This was lesson 13, which in our textbook is section 4.1. Now, if you're not able to figure out the domain or the domain's not a closed interval, an alternative approach would be to use the first derivative test for absolute extrema and the second derivative test for absolute extrema, which we'll talk about in this lesson. They're just little twists on the first derivative tests for local maxes and mins that we've already learned, right? So you've got two options, right? If you know the domain, you're going to use the closed interval method. How about we get a different color? Right? If that domain is a closed interval, then you can, and the function is continuous, which they're all going to be, then you can use that closed interval method. If the domain isn't a closed interval, remember closed intervals are just A to B. In other words, A less than or equal to X less than or equal to B. If we don't know the domain, or if it's not a closed interval, then we're going to do one of two things. You can either do the first derivative test to find the absolute extrema, a twist on it, or the second derivative test to find absolute extrema, which we're going to show in here. Now, we do have technology, right? So you know what your objective function is. We can use a graphing calculator like Desmos to go ahead and find the absolute max or min for that function. And then we congratulate ourselves, right? Because word problems can be a little intimidating. Let's go ahead and jump in and do example 1. A car company charges its customers P dollars per day to rent a car, where 45 is less than or equal to P, which is less than or equal to 200. Now these might seem like they're kind of coming, this domain here that's being given to us might seem like it's coming out of nowhere, but you can imagine that there's like a fixed price that I have to charge for each rental so that I break even. You know, there's a cost of business, and so maybe I have to charge at least $45 to break even. And then there's a max price that is, if you charge beyond that, you're not going to get any business. All right, so that's where those numbers are kind of coming from. The number of cars rented per day can be modeled by this linear equation. The number of cars is equal to 800 minus 4p. So here n is the number of cars rented per day. How much should the company charge each customer to maximize the revenue? Now I see the word maximize the revenue here. That's the function that is my objective function. And in this case, I want to maximize it. Revenue is the amount of money that you are bringing in, whereas profit, you have to subtract off the cost of business. Okay? So just take a second to read through this problem one more time. I don't think a picture is applicable here, so we're going to want to start introducing our variables. Okay? So I feel like we've understood it. Now it's time to define our variables. All right, so I'm going to let P be the price of the rental, right? What the company charges to rent the car. I'm just going to use dollar signs of the rental. They've introduced some notation for me. And in fact, actually, let's just mention this domain restriction. 45 less than or equal to P less than or equal to 200. That's nice that they gave us that. N here is a function of P, but let's just say what N stands for. N is the number of cars rented each day. Yellow. And then how about R for revenue? How about a big R? All right, so we've introduced some notation. The next thing for us to do is to relate our variables. We need our objective function, that's going to be our revenue, and then a constraint equation that'll allow me to write the revenue in terms of just one variable. Let's do that part. Right? So my objective they used the word maximize there. is the revenue. And the question that they're asking us is, what should the price be so the revenue is maximized? So I want to write revenue in terms of my price. In other words, I want to write revenue as a function of my price. Now, what is revenue? Revenue is the number of cars that you rent say I rent 10 cars for $45 each. What would my revenue be? It would be the number of cars 10 times the $45 times the price per car. So I would be bringing in 10 times 45, I would be bringing in $450. All right, so revenue is equal to number of cars rented times the price per car. Now, this was our very first problem, and my constraint equation is given to me. Okay, and let's just see that this makes sense. The number of cars that we can rent would be the maximum 800, right? If P, I'm not charging negative dollars, right? I'm charging positive dollars. So if P was 0, if I was given all the cars away for free, the number of cars that I could rent out for no money would be 800. In other words, this car lot probably only has 800 cars, right? And then the more that I charge, the less that I'm renting out. And there's a point at which I'm charging so much that I don't rent anything out at all. So our constraint equation was given to us. They told us that n of p, and maybe you don't like the function notation, maybe we just write n equals 800 minus 4p. Oops. 4p. All right, and so now I'm going to substitute that into my revenue. My revenue, in fact, maybe I'll just squeeze a little. I've got it all written here in English, but maybe we just write it in math. My revenue is the number of cars rented, n, times the price per car, p. So if you make this substitution, now R is going to be written just in terms of P. In other words, R is a function of P. My revenue is a function of the price that I charge per car. So here's my objective function now. As a function of one variable. I'm not going to write that. I'm just going to say that. My objective function now is R is equal to 800 minus 4p times p. We can write, if we go ahead and distribute, R is equal to 800p minus 4p squared, and we have this given domain restriction that the price that I charge has to be strictly, or not strictly, it has to be between 45 or 200. All right. So what do we have? we have a function that is continuous. R is a polynomial. It has no domain restrictions. It is continuous everywhere. And it's continuous on a closed interval. So by the extreme value theorem, my revenue, R, absolutely achieves a absolute max and an absolute min. I am interested in the absolute max, and I'm going to use the closed interval method to find it. All right, so let me just write down what I just said. All right, since R is a continuous function, it's a polynomial, check. Defined on a closed interval, check. We can use the closed interval method to find its absolute max and its absolute min revenue, but this problem specifically calls for absolute maximum. Let's just go back and remember what the closed interval method looked like. What you needed to do is find the critical points in that open interval. Those are places where the first derivative is either 0 or undefined. You then went ahead and found the function values there, the y values there. Our function here is revenue, so we'll find the revenue at that critical point, p being a price. We'll find the function values at the endpoints. That's our 45 and our 200 respectively, and then we compare. Hopefully, for this particular model, my critical point is where we're going to have our absolute max, because we don't want to just be staying in business. That would be a bad business model. All right, so let's go ahead and do it. And I'm going to insert a page here. All right, so let's go ahead and use the closed interval method here. So step 1 for that is to find the critical points. Here's my revenue function, 800p minus 4p squared. The derivative is 800 minus 8p. There are no domain restrictions here, so there are no places where the derivative is undefined, but there is a place where the derivative is 0. Okay? And factoring out that 8 times 100 minus p equals 0, we see that we have a critical point of p being 100. All right, p equals 100 is our critical point. The second step is to go ahead and evaluate the revenue at that critical point. Evaluate R at the critical point of P being 100. Okay, so my revenue, if you wanted to write R of 100, you can. I'm just going to write R is 800 times 100 minus 4 times 100 all squared. So we've got 80,000 minus 40,000. We have R is 40,000. And this is money. Yeah, we can put that in at the end. So this is a potential absolute max. But we have to evaluate, because there was a domain restriction for the price of the rental, we have to evaluate the revenue at those endpoints. This is a potential absolute extrema. All right, so now I'm going to evaluate the revenue at the endpoints. just going to do PTS for points. And that was the 45 less than or equal to P less than or equal to 200. So I'm going to go ahead and stick in the 45, and then I'll stick in the 200 and see where the revenue is. R of 45 is 800 times 45 minus 4 times 45 squared. And I've got a graphing calculator here. I've calculated that already. R of 45 is equal to 27,900. That's a potential absolute extrema. And now evaluating the revenue at 200, we get 0. And step 4 is to compare those potential absolute extremas, those potential absolute revenue values. Compare. That's RE. Your teacher can't spell. I don't know. So we've got that R is 40,000. R is 27,900, and R is no money. The biggest Y value here is the absolute max. 40,000. The smallest Y value is the absolute min, and this is a nice model. This person can't lose money. It looks like they can only break even. Well, actually, they lose money in terms of profit. The max revenue they can bring in is, or minimum revenue, sorry, that they can bring in is they can bring in nothing, right? So what's going on here is that if at these endpoints of 45, my revenue is 27,900, that lower bound here is probably the cost of business. That's him breaking or her breaking even. And then this upper bound of 200, well, if I'm charging $200 for my car rental, that's just too much. The market won't bear that. Nope, my revenue is going to be 0. I'm not going to be renting any cars whatsoever. Okay, so here we have it. In conclusion, the revenue is maximized when the price to rent each car is $100. That was that critical point. Seems kind of expensive. I don't know. I haven't rented a car. When the price is $100, the absolute revenue is 40,000. Okay, let's go ahead and graph it. All right, so here's my revenue function. There's R of the 45 being 27,900, R of 200 being 0. And notice that this thing is a quadratic. And oh my goodness, some of you probably thought Lindsay is doing all this calculus and she doesn't need to. Because I know a quadratic opening down has a max, and the max occurs at the vertex. So alternatively, you could have just used some algebra on this problem. But it's a good entry-level problem for us. I hope I've outlined the methodology thus far.